Welcome to Rex. In this video, we'll be learning about how to create a logistic regression model using Rex. Logistic regression attempts to model the relationship between a dependent variable and an explanatory variable by fitting a logistic function to observed data. Here, the dependent variable has a binary outcome, such as success and failure, or yes and no. Let's first take a look at our data. In this dataset, the following data was obtained for 1,822 colon cancer patients. The disease status variable, where 1 indicates those with cancer or those who have died due to cancer, and 0 indicates controls. The age of the patient in years, the presence or absence of intestinal obstruction, where 1 indicates the presence or absence of colon cancer cell adhesions, where 1 indicates presence, the number of lymph nodes with confirmed cancer cells, the patient's biological sex, where 1 indicates male and 0 indicates females, and lastly, the type of treatment that the patient received, where 0 indicates controls, 1 indicates levamisole, and 2 indicates levamisole plus 5-fluorouracil. Let's say we want to analyze the relationship between colon cancer and these explanatory variables. In order to run our analysis, we first select our data, go to Regression, and Logistic. We'll first be using this Variable tab to define the dependent and explanatory variables. As we can see, the headings in the first row of the Excel datasheet are displayed under All Variables. We can use the arrow buttons to add or remove variables from each option. Let's first select the variable of interest, disease status, as a dependent variable. We then select 0 as the reference level that indicates controls who do not have the disease. Next, we will select obstructions, adhesions, the patient's sex, and the treatment type as our categorical explanatory variables. We will select the patient's age and the number of lymph nodes with confirmed cancer cells as our continuous explanatory variables. We will click Main Effect to include all 6 explanatory variables as main effects in the model. Lastly, we will select Logit as the link function to fit the model. Next, we go to the Validation tab. In this tab, we decide how to divide the data into training and test data. Here we will use Rex's default options, which validates the model once by partitioning the data into training and test data, then uses all the data to fit the regression model. Next, we go to the Output tab. We will use this tab to select statistics, tables, and plots to output. Additionally, we can use the Export section to export statistics directly into our Excel datasheet. First, we want to output the confidence interval of the regression coefficient estimates at a confidence level of 0.95. We also want to output our variance influence factors and the exponential transformations of the regression coefficients. Next, we want to output an ANOVA table for the regression model that uses the Type 3 method to calculate the sum of squares. We also want to output a classification table of the observed and predicted values of the dependent variable. We click Goodness of Fit test to perform a likelihood ratio test that tests whether the current model is statistically different from the null model without explanatory variables. Next, we want to output a receiver operating characteristic curve based on the predicted probabilities and the observed values of the dependent variables. Lastly, we select Simple Logistic Regression to output a regression table of the simple logistic regression of each variable. In this next section, we can select the training data statistics to save in our datasheet. Here we will select the fitted probabilities predicted by the final models, along with their confidence intervals at a 0.95 confidence level. We also want to select the fitted groups predicted by the final model. Next, we will go to the Variable Selection tab. We check Variable Selection to automatically select the variable corresponding to the optimal model based on the ACA-IK information criterion. We then select Forward for the variable selection method. Lastly, the Graph tab can be used to output a nomogram for the model, but today we will choose not to. Once we are done setting up our analysis, we can click OK. As we can see, the training data statistics that we decided to output are saved directly inside of our Excel datasheet. Additionally, once the analysis is complete, a window pops up with the analysis results. Let's take a look at our results. First, let's take a look at the coefficient estimates. The sign of each coefficient indicates the direction of the relationship between the explanatory and dependent variables. The coefficient value itself represents the mean change in the logarithm of the odds ratio of the dependent variable given a 1-unit change in the explanatory variable. This is assuming all other explanatory variables were fixed. For example, let's take a look at the regression coefficient for the nodes. Here, the coefficient is 0.1931. This means that the model estimates the log odds of disease or death increased by 0.1931 on average for every 1 increase in the number of lymph nodes with confirmed cancer cells. Next, we can see the odds ratio itself. For the nodes, the odds ratio is 1.2130, indicating that the odds of death or disease was 1.2130 times higher for every 1 increase of lymph nodes with confirmed cancer cells. Next, let's take a look at the p-values. We can use the p-values to verify whether the estimates are statistically significant. The p-value for each term tests the null hypothesis that the coefficient is equal to 0, which means that the explanatory variable has no effect on the dependent variable. At a 95% confidence level, p-value less than 0.05 indicates that you can reject this null hypothesis. Here, we can see that the p-value is less than 0.05 for the effect of obstructions, adhesions, as well as nodes. This indicates that the effect of these variables are statistically significant. On the other hand, the p-value is greater than 0.05 for the effect of the patient's age and the patient's sex, indicating that the effect of these variables are not statistically significant. When compared to the control treatment, the p-value is greater than 0.05 for treatment 1. However, the p-value is less than 0.05 for treatment 2. This means that compared to the control, the effect of treatment 1 was not statistically significant, but the effect of treatment 2 was. Lastly, let's take a look at the variance influence factors. These values are indicators for diagnosing the multicollinearity of explanatory variables. In general, a VIF above 10 indicates high correlation and is a cause for concern. As we can see, the VIF is less than 10 for all of the explanatory variables, indicating that there is no to low multicollinearity. An ANOVA table indicates whether the regression model is statistically significant and how well the model fits to data. Here we can see that the p-value is less than 0.05, indicating that the model is statistically significant. The Type 3 sum of squares table indicates the significance of variable effects for categorical explanatory variables with 3 or more levels, such as our variable for the treatment type. Unlike the table of coefficient estimates, which showed whether the effect of each treatment type was significant, here the Type 3 sum of squares table shows that the overall effect of the treatment variable itself was significant. A classification table, also known as a confusion matrix, indicates how the observed and fitted values of the dependent variables are distributed. The true positives, the true negatives, the false positives, and the false negative values, as well as various related statistics, are displayed. The receiver operating characteristic curve is a graph based on the predicted probabilities and the observed values of the dependent variable. This curve plots the true positive rates against the false positive rates at different cutoff points between 0 and 1. The area under the ROC curve, or the AUC, provides a measure of performance across all possible classification thresholds. While a model whose predictions are 100% wrong has an AUC of 0, a model whose predictions are 100% correct has an AUC of 1. Here we can see that our AUC is 0.686. Overall, as we have seen in this video, the logistic regression model helps us analyze the relationship between a binary dependent variable and an explanatory variable. Thank you for watching today's video in Statistical Analysis in Rex Pro. Don't forget to like and subscribe to RexSoft's YouTube channel for more informational videos on statistics, data, and how to use Rex.